So now that I have a system of equations, let us solve for all possible solution vectors. So consider the augmented matrix representation of our system of equations. One, two, 0, 0, 0, 0, 0, 1, minus 3, 0. Now, note this matrix is in echelon form. We have two free variables, x2 and x4, or in this case, it's going to be A, B, and D. And two basic variables. A and C. Let B equal T, which is a real number, and D equal S, which is a real number. What am I doing? I am letting my free variables be free. Then, using the system of equations, A equals minus 2t and C equals 3s. Let updating our solution vector gives v equals minus 2t, 3s, t, s, which equals minus 2t, 0, t, 0, plus 0, 3s, 0, s, which equals t minus 2, 0, 1, 0, plus s, 0, 3, 0, 1. And what have I done here? I've taken the solution vector and I've split up and separated the vector using the addition to be the scalar times one vector plus the scalar times the other vector. Now, these are the solution vectors, but what matrices do they represent? Well, we have to convert these vectors back into matrices. So thus, x equals t minus 2, 0, 1, 0 plus S 0, 3, 0, 1, where T and S are elements of the real number. So we've created a solution for all possible solutions to this system of equations are represented by this combination. As our vector ABC is a solution, it must equal a linear combination of these vectors. So X equals some linear combination T of S. We don't know which T and S they are, and they're not any T and S and R. But this is where they are some real numbers. We don't know what the real number is, but because of this, therefore, W is a subset of the span of the set of matrices minus 2, 0, 1, 0, 0, 3, 0, 1. So that set of matrices, this set of matrices here, W is a subset of that set of matrices. Let S equal the set minus 2, 0, 1, 0, 0, 3, 0, 1. Then W is a subspace of the span S. What have we done up to this point? We have shown that we have shown step 1. We have created an S such that W is a subset of S. Awesome. First step, check. The next thing that we want to do is we want to show that the span of S is a subset of W. So while a lot of people will try to figure out what's an elegant way to do this, what's a nice way to do this, what I find easiest is just simply prove it the way you show one set is a subset of the other. Let X be an element of the span of S, take a general linear combination, show that that general linear combination satisfies the condition. So we're going to do that over here. Let's zoom in over here. Let X be an element of the span S, then X equals S 2, 0, minus 1, 0, plus T 0, 3, 0, 1. Just gonna recenter and zoom in over here, where S and T are elements of the real numbers. Then X equals 2S 3T minus S T. Note that 2 times that 2S plus 2 times minus S equals 0, and 3T minus 3 times T equals 0. Therefore, X is in W. Thus, the span of S is a subset of W. Therefore, as W is a subset of the span of S, and the span of S is a subset of W. S, the span of S equals W. This showing that X being an S means that X is in W is typically a really easy step. If you've calculated your set S properly, this should be very straightforward. At least for the questions that we're seeing. Once you've created that set S, showing the span of S as a subset of W isn't too hard. Now, we need to show S is linearly independent. And the way that we can do that is we can take the two vectors, take a linear combination equaling the zero vector. Consider A 2, 0, minus 1, 0 plus B 0, 3, 0, 1 equaling the zero matrix. And then 2A equals 0. 3B equals 0, minus A equals 0, and B equals 0, which implies that A equals 0 and B equals 0. Therefore, the only solution is the trivial solution. That is to say, S is linearly independent. I showed it was linearly independent by showing that the zero vector is represented uniquely using the two vectors in S. So that is to say, S is linearly independent as the zero vector is represented uniquely by S. And to finish it all off here, we have as S is linearly independent and a spanning set for W, S is a basis for W. The last thing we need to do now is we need to calculate the dimension of W. And to calculate the dimension of W, we simply count the number of vectors in W. Okay, so, or in S. The dimension of W equals the number of elements in S, which equals, we look at the set S. Here there are 1, 2 matrices, so it equals 2. So the dimension of our subspace is 2.